Okay.
It's problem 72.
Okay. Let's see if I've got that one. Okay, it looks like I do.
Yeah, I was having trouble just figuring out which one to use. I guess when I went through, we did this one in the lab, N2O.
Okay, can decompose, use bond dissociation enthalpies. Okay, so you know that the equation we're going to use. Can you see what the problem as written?
Yeah.
Great. Okay, so if we're going to use bond dissociation enthalpies, we're going to say that the enthalpy change for the reaction is going to be the sum of the bond dissociation energies of the bonds that are broken, because those are the ones that require a positive amount of energy, minus the bond dissociation energies of the ones that are formed. So with the minus in front of it, this amount of energy that would be normally be required to be for breaking the bonds is now the energy that is produced. Okay, so the reaction is N2O, gives us 2N2 plus O2. And we're going to need our, whoops, I made a mistake. We're going to need our Lewis structures. Now this does have two Lewis structures. And here we've got a 0, a +1, and a -1. And here we've got a -1, a 0, and a 0. Nope. +1. Okay, and we have N2. And then we have O2. So we could use this structure up above to figure out what's going on, or this one below what's going on. And rather than do them both, let's decide which one would be a better one to use for this exercise. Which one do you think would be better?
The top, because oxygen is more electronegative than nitrogen.
And in the top one, there's a -1 charge on oxygen, which is what we want. So we're going to do it for the top one, okay?
Okay.
And I'm just going to put a line through that. We can come back and do this one in a bit, but let's just work on this one here. So we have, for the bonds that are being broken, we have 2 nitrogen-nitrogen triple bonds, 1 here, but since we have the coefficient of 2, that really means 2 total, okay? And then +2 for the nitrogen-oxygen single bond. So those are the ones that are broken, and the ones that are formed are the nitrogen-nitrogen triple bond, but there's 2 of them. And here we have 1 oxygen-oxygen double bond. Now, I don't normally do this, but you can see that these 2 cancel each other out, right?
Right.
So I'm going to leave them out. And I'm going to do, well, actually, I'll put them in at first, but then I'll take them out later. So this is on like page 398 or something like that, the dissociation energies.
392.
Yep, there they are, 392. You're right. So the nitrogen-nitrogen triple bond is 945. The nitrogen-oxygen single bond is 201. And then I'm going to do 2 times 945 kilojoules again. And then the oxygen is 498. So you can see this really amounts to 402 minus 498, which is going to be what?
Negative 100.
Pretty close to negative 100. And when we do all the work and all the whiz bang stuff, it's going to be, oh, I don't like this. It's going to be negative 96 kilojoules. But because of this right here, and this right here, this times 945 would be 1,890, which is good to there, which means we have to round to the tens, which means we have to round there, which becomes negative 1.0 times 10 squared kilojoules. And that's the only way to write this rounded to the tens. Okay?
Okay.
All right. So that would be the answer using this resonance structure. Out of curiosity, I want to see how different it is using this resonance structure. So how would things differ here? We'd have 2D N double bond plus 2D N double bond. Only double bond to nitrogen, double bond to oxygen. Everything else would be the same. So when we look up these values for a nitrogen-nitrogen double bond, it's 418. And for a nitrogen-oxygen double bond, it is, well, I don't see any listed, so that means we can't do it. So clearly, we can't complete this method because this is not listed in our book. So this is what they had meant us to do right here. Okay?
Okay, so we should just choose the best resonance structure for these ones.
Well, in this case, that's what we have to do because we can't look up a bond and a half for nitrogen to oxygen, and we can't look up a 2.5 bond for nitrogen to nitrogen. So you have to use the best resonance structure.
Right, okay.
So any questions about this one?
No.
Okay. So that was number 72. Okay, what next?
Let's see. Number 78. I went through and did even ones because I thought maybe you'd go through them. I probably should have done odds.
Actually, I have the even ones, most of the even ones written down. But I've been focusing more on students asking questions in these study sessions. So which one was the next one?
78.
78. Let's see if I have that one written down. Oh, 78 I don't have written down, so we'll have to look at the book. Okay. And 78 is not written down because it's a long one. Okay, the formula for nitrile chloride is ClNO2, in which the nitrogen is the central atom. Draw the Lewis structure for the molecule, including all resonance structures. What is the NO bond order? Describe the electron pair molecular geometries and give values for all bond angles. What is the most polar bond? Is the molecule polar? And here is the electrostatic potential surface. Identifying the atoms A, B, and C in this molecule. Okay, so here, one way we can identify these just from the get-go is red is negative. So these red atoms are the 0.03. No, I take that back. The red atoms are B because that has the biggest negative value. Do you see that?
Yeah, it's kind of a little bit washed out, but
Here, let me try to zoom in just a little. Okay, so red means negative,
right.
and green means positive, and so does blue. Basically, the way the colors work is Vibgyor, where red is the most negative and violet is the most positive. So based on these, do you see that the central atom has to be C?
Yeah, and the red ones are the oxygen,
Well, the red ones are B because that's a negative 0.26,
the most electronegative.
and the yellow one has to be A. So in terms of what we have going on here, the only atom here that has two oxygens, or the only element with two of them, is the oxygen. So these red ones are clearly the oxygens. And we can make sense of that two ways. One is that the formula has two oxygens in it, and two, this has two red spheres in it, so they have to be oxygens. Furthermore, oxygen is the most electronegative atom out of all of those. And so therefore, they should have the reddish tinge next to them. Now, as far as chlorine and nitrogen goes, if we look at the electronegativities, we're going to find out that they don't differ that much. So let's see, where are the electronegativity numbers? Here they are. So they actually have chlorine being slightly more electronegative at 3.2 and nitrogen at 3.0.
Oh,
Okay.
okay.
I remember chlorine as being 3.0, and bromine is 2.8, but that's a different book that I was looking at. So knowing that these numbers are this way in our book, we expect chlorine to be slightly negative compared to nitrogen. So based on that, we expect that the yellow sphere, wow, that's kind of neat looking in the video here. It's almost like it's sparkly. All right, nonetheless, sorry I got distracted. This yellow sphere is going to be chlorine, and this blue sphere is going to be nitrogen based on what we saw before, okay?
Right.
Okay, so let's go ahead and first get the Lewis structure. So this is number 78. And I need to zoom out a little. Okay, so we have ClNO2. And they say nitrogen is the central atom. That's another reason why when we look at that drawing, the blue one is the central atom, so that has to be nitrogen. letter E is kind of an interesting question on this one because you can answer it without knowing anything almost. Okay, so draw the Lewis structure. Nitrogen's going to be in the middle. Oxygen's on the flanks. When we count valence electrons, it's going to be 7 plus 5 plus 12 for a total of 24. So that's what we're going to have at the outset. And then we want to make a double bond to nitrogen so that it can have an octet.
Right.
And there's two ways of doing that.
So I made 3 and then I got rid of the one with chlorine. I shouldn't have done that.
Well, yeah, chlorine doesn't normally make double bonds, so I wouldn't write that one down.
Okay.
A lot of times I'm making the structures I want based on the number of bonds they normally make or could make.
Okay.
And so here, no matter what you do, nitrogen's not going to go with the normal 3 bonds. So that's okay. But yeah, if you did write that one down though, so I'm going to go ahead and write that one down.
I see though that chlorine doesn't normally do that.
No. If you look at formal charges, we'd have a -1, a +1, a -1, and a +1.
That's why I got rid of it.
Yeah, and you want as many zeros as you can get.
Mm-hmm.
And here you'd have a -1, a +1, a 0, and a 0. And so you've got 2 out of 4 being zeros, and that's good. And you'd have the same thing over here, except for the oxygens would be opposite of what they are here.
Right.
So we really don't want to include that because it's a clearly inferior to these two.
Right.
Okay, so for A, draw the Lewis structure, that's what we get. So B, what is the NO bond order?
I said
So
1.5.
Yeah, this is one of those ones where you could look at either resonance structure and look at those two and get the right answer. Because these resonance structure only differ by where the double bonds are on the oxygens.
Well, you could also do 3 + 3 divided by 4 if you want to do it the same way.
No, you can't. This is the way you are supposed to do it. We're supposed to understand that neither of these resonance structures is correct by itself, but they are correct together. Because this oxygen that I'm pointing at is this oxygen also. They are the same oxygen, not like twins, but rather the same oxygen, looking at the electrons being spread out a little bit differently. Are you with me here?
I just don't see why we can't do that because it equals 3/2 too.
Well, if these oxygens are identical, they're not identical. They are in fact the same oxygen.
But it's not the same as the one on the other side, is what you're saying.
No. So look at this. Is this oxygen that oxygen?
No.
No, they're not, because I have them written down separately, right?
Right.
But with resonance structures, every atom is the same atom. So these are not 2 oxygens, they're 1 oxygen.
So don't take the shortcut, even if it gets the same.
And you see these 2 nitrogens, they're not 2 nitrogens, they are the same nitrogen.
Okay.
And you see these 2 oxygens,
Mm-hmm.
they are not 2 oxygens, they are the same oxygen.
Right.
Okay, so these are almost like snapshots of the molecule at different times, except they're not even that.
It's just what it might be.
No, it's not even what it might be. It's just a way for us. Well, let me draw the molecule the way it really should be drawn, but we can't do that either. Okay, you see how we have 3 bonds here?
Yeah.
And you see how we have 6 electrons and 4 electrons?
Uh-huh. That
So,
aren't bonded.
what's that?
The ones that aren't.
One more time?
The electrons that aren't bonded.
Yeah, the non-bonding electrons. There's 2, 4, 6, 8, 10.
Uh-huh.
So if we wanted to make this as even as we could, this is what we would do. 1 electron there and 1 electron there. So that is kind of like 2, 4, 6 electrons, right? 2, 4, 6.
2, 4, 6. Yeah.
How do we spread 10 electrons over these 2 atoms? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that's what the molecule really kind of looks like, but we can't draw this. And the reason we can't draw this is that when you have a single electron like this, or this, or this, or this, it's called a free radical. And free radicals are extremely reactive. They're bad, bad, bad molecules. And this is not a free radical. There's no single electrons anywhere. So that's why we can't draw this. It's inappropriate. So what I'm trying to tell you here is that if we can't draw this for the molecule, then what we do is we draw this, and we kind of say it's an average of the 2.
Mm-hmm.
Okay?
But that doesn't necessarily mean that they are always in a free radical state if they have the 1.5 bond.
Oh yeah, if you have a single electron, it's a radical. That's all there is to it.
So this will always be, this ClNO2 will always be a free radical? Will the
No,
molecule?
that's what I'm saying. It is not a free radical. It is not. So we can't draw it this way.
Okay. So how would you know if it is or not?
Well, the way you really end up with free radicals is if you had an odd number of electrons, and we don't.
Okay.
So unless you have an odd number of electrons, you're never going to assume you have a free radical.
So that it doesn't happen often.
No, it doesn't happen often.
Yeah.
So this is what we have to draw here. It's an average of these 2. So this one is not right. This one is not right, but when you average them, it is correct.
Okay.
It's kind of weird, but that's the way it is.
So then if it said a single bond between nitrogen and oxygen is 100 picometers and a double bond is 90 picometers, would you add the 2 and divide by 2 to get the length, the average length of that bond?
Yeah, that's what you would do. You'd say that bond is probably between an oxygen nitrogen single bond and between an oxygen nitrogen double bond. So here is that's not one of the questions, but B is what is the NO bond order? So let's finish that one off. The NO bond order, you're going to see right here where I'm pointing my fingers.
Mm-hmm.
That's 3 divided by 2, right?
Yeah. So there's 2 different bond orders.
Well, it turns out they're exactly the same. So what's this one?
3 halves.
3 divided by 2. So the bond order is 3 divided by 2 no matter which way we go. So a bond and a half. Okay, so now if we wanted to get the actual bond length, so the NO bond length, this is what we can say without knowing any numbers. That the NO single bond is going to be longer than our NO bond in ClNO2. And this is going to be longer than an NO double bond. That's what we expect. So did you read these numbers to me?
No, I just made them up.
Oh, you made them up. Okay. I thought maybe you were reading them from somewhere. And actually, maybe they're on page 392 or whatever. Let's see. Well,
Oh,
those are bond strengths. An NO double bond is 115 picometers. And an NO single bond is 132 picometers. So your numbers that you invented weren't so far off. So we would expect this to be somewhere in the middle.
right.
So here, halfway between these would be, let's see, 32 minus 15 is 17. Half of 17 is 8 or 9, whichever you want to call it, 8. So 115 plus 8. So this is 123-ish picometers.
Right. And
That's
that's
what we-
technically
we
the
expect.
length of both of them.
Yeah, they're both 123.
And that's just because their bond orders are equivalent.
Yes, that's exactly right. Okay, so C is describe the electron pair and molecular geometries and give values for all bond angles. Okay, so there are 3 pair.
Mhm.
So I'm going to draw it like this. This is the electron pair geometry. And we're going to call it trigonal planar. And what are the angles?
120.
120. Now let's do the molecular geometry. So I'm going to put the nitrogen in the middle. I'm going to put the chlorine at the top. And we don't need to draw both of these. We can draw one or the other, because they're going to look identical, except the double bond is going to be on the other oxygen. So what do we call this for molecular geometry?
Trigonal planar.
Yep. And what are the angles?
120.
Yep. So that's C. Now letter D says, what is the most polar bond in the molecule? So we're supposed to memorize fluorine is 4O, oxygen is 3,5, nitrogen is 3O, carbon is 2,5, and we just saw that chlorine was 3,2, right?
Yeah.
Okay, so when we look at the most polar bond, we're looking for the biggest difference.
Mhm. It's the
So nitrogen, oxygen, what's the difference?
0.5.
Okay, nitrogen, chlorine, what's the difference?
0.7 or 0.2.
0.2.
Yeah.
And this nitrogen, oxygen, what's the difference?
Well, will it?
0.5. Bond polarity has nothing to do with how many bonds you see there.
Okay, so does it mean since the oxygen on the left has one more electron, that's technically the more electronegative oxygen of the two?
Absolutely not, because remember, these bonds are both 1.5, so they both have the same number of electrons.
Okay.
Okay, so what is the most polar bond here?
The NO.
Right, the nitrogen-oxygen bond is most polar. And notice I did not write NO single bond, I did not write NO double bond, just the NO bond. They're
Right.
both the same polarity, 0.5s.
Well, they're the same bond too, right? Technically.
They are, not technically, they are. Like if you study this molecule and use any sort of spectroscopic technique, you will find out that both of these bond lengths are exactly the same. And they do not get shorter and longer and shorter and longer. They're the same length all the time.
Okay.
I'm kind of lying about that, but for all practical purposes, they do waver like a picometer, but that's because of what we call bond vibration and stretching. Okay, so if we draw that molecule, we've got the the blue dot in the middle. We've got the red dots here, and then we've got the yellow dot here, right? So
Right.
here's our blue dot. Here's our red dots. And when we draw the little drawing around here, this has a red tinge here, this has a red tinge here, this has a green tinge here, and this has a blue tinge in the middle, right?
Right.
And when we look at Vib Gyor, we know that red is going to be negative and violet is going to be positive, if anything, right?
Right.
So based on this, we know that these guys are negative, and this one up here being green is going to be in the middle, and the blue one is the most positive one. Now, the problem reads in A, it says nitrogen is the central atom. So we know that's nitrogen, period. Right?
Right.
From the formula, there's two identical atoms, which must be the red ones. So that's got to be an oxygen, and that's got to be an oxygen. So what does that leave this guy being?
Chlorine.
Chlorine. Okay. Now, when we look at the numbers, when we say A, B, and C, they say that A is negative 0.03, B is negative 0.26, and C is plus 0.56. So which one of these is nitrogen?
The middle, the lowest, the highest one.
So C is
The left
nitrogen, right?
Yeah.
Now, which ones of these atoms are B's, and why am I choosing B next?
It's the most electronegative.
Right, so those must be the oxygens, right?
Yeah.
And there, that leaves A being chlorine. So this molecule is definitely polar. And if we drew a polar symbol next to it, it'd look like that. Pointing to your most electronegative atoms, oxygen.
Right.
Now, were you at that earlier session where I was talking about walking the dog?
No, that must have been in the morning.
I thought it was in the afternoon with Charlotte. But Charlotte likes to use vectors to figure out the
Oh,
polarity.
yeah, yeah.
And
Okay,
so
now I remember.
here you would do this for the vectors, as you would call it.
Yeah.
And here you would do this for the vector. Now, why is this such a short little vector compared to these?
Because the chlorine's not pulling the nitrogen as hard
Yeah.
as oxygens.
This is a 0.2 arrow, this is a 0.5 arrow, and this is a 0.5 arrow.
Right.
Okay, so here you got two German Shepherds dragging you this way, and you've got this little dachshund pulling you that way. Which way are you going to be going? And the answer is this way.
With the big dogs.
Yeah. Why aren't you going to the left or the right? And the answer is because even though the big dogs are dragging you in opposite directions, they're not going to rip you apart. So you'll end up just going straight down and so forth. Okay.
Okay.
But we don't need to walk the dog. We can say, hey, the oxygen is the most electronegative. So we're going to point the arrow in their direction from the other side of the molecule.
But these don't actually move anything.
No, see, the deal here is this arrow does not indicate that the molecule is moving. It indicates that this side of the molecule is positive and this side is kind of negative. That's all.
Okay.
So we do this instead of this. So that's one of the problems with the arrow is when you draw the arrow next to the molecule, people think that the molecule flies through space like Superman or something. with its arms spread apart and here's its legs. That's not the case. The
So
arrow simply indicates which side is positive and which side is negative.
does the electronegativity have anything to do with like the structure of things too when they're in like lattices and stuff?
I'm not sure what do you mean by lattices?
Like why does the negativity and the less negativity have anything to do with like orientation?
No. What we use to decide the orientation is just that the electrons in the bonds are repelling one another.
No, like if there's multiple molecules together of the same type.
Yeah, sure. Electronegativity and bond polarity totally informs us on whether or not they're going to stick together very well or not. So if you have something that's slightly negative and slightly positive, and you have another one that's slightly positive and slightly negative, and let's say that they come together, what's going to happen is this. When they come together, this guy's going to rotate so that they have these attractive forces like that.
Mm-hmm.
Opposites attract, right?
Right.
So why would these things butt up against one another like this when that would repel? And the answer is they wouldn't. Or maybe this doesn't rotate and what they do is this. You see, it doesn't have to rotate. We still have opposites attracting, right?
Mm-hmm.
And then guess what? If another one came in here, what would it do? Slightly positive next to that and slightly negative. And look, we've got a little network.
Mm-hmm.
Okay.
Okay.
So yeah, when they're together, things that are polar tend to stick together better than things that are not polar.
Right.
So that means that when you look at molecules like CH4 versus NH3, CH4 is totally non-polar.
I mean, what about even water? Just the
Water also, but water, there's something else going on with water. So that's why I left it out.
Okay.
So this guy weighs 12 plus 4. This guy weighs 16. This guy weighs 14 plus 3. This guy weighs 17.
Okay.
So in other words, they weigh about the same amount. They're about 10% apart. Now I'm going to do a little search on the internet real quick. And what I'm looking up here is I'm looking up the boiling point of methane. And I'm just going to put boiling point of CH4 and NH3. And so their boiling points are this guy is minus 33 degrees Celsius. This guy is minus 164 degrees Celsius. Do you see how different they are, even though they only differ by a mass of 1?
Mm-hmm.
That's not normal. So why do these guys take so much more energy to separate from one another?
Their bonds are stronger.
Because they do this.
Oh, okay.
Now,
So because they're more polar.
Because they're more polar. If you look at these guys, this is kind of what they do. So nitrogen is more electronegative than hydrogen. Okay.
Mm-hmm.
So you got this kind of slightly negative inside, right?
Right.
Okay. So when these two come together, is there any way for this guy to rotate or move around so that when they come together, the negatives and the positives come together?
No, no,
No, because the negative is on the inside.
right.
So that negative can't be attracted to this positive because that's on the inside.
Mhm.
So these guys, these electronegativities are not so great to make this really nonpolar. But the deal is that these positives will kind of repel one another, and that's why they don't want to stick together. That's why they boil at such a low temp.
What is CH4?
It's methane, and NH3 is ammonia. And you've heard of methane before, right?
Well, methane gas. I
Yep,
have.
methane
That's
gas. It's
why
what,
it doesn't stick together because the gas
yeah,
doesn't stay together. It's
doesn't,
spread out.
yeah, it's because the gas molecules are nonpolar, so they don't really stick together that well.
Okay.
And this is the stuff that cows make. It's true.
Right. They make a lot of it.
Yeah, people have even thought about, is there a way to harness that,
Well, actually, there's this like I forgot what it's called, like a fermentation chamber that some farmers use. I forgot what it's called, but if they have like a ton of head of cattle, a bunch of them, I don't think they do it in the United States, but they make like a biofuel out of the organics in a
Oh,
vacuum.
yeah, but I don't think they're having the cows fart into the machine or something.
No, they're just collecting.
You're going to have a really well-trained cow to do that. Okay, so that's number 72.
Yeah, there's a lot in these questions at the end. I think they're good for studying.
Oh yeah, absolutely. Did you want to do another one?
Sure. I got up to 78, but I didn't do any of the odd ones.
Okay, well, let's see. How about 75? It's got a triangle next to it, which means it's a humdinger.
All right.
It means it's a really, really hard one.
Mm-hmm.
Okay, the cyanate ion has the least electronegative atom carbon in the center. The unstable fulminate ion has the same molecular formula, but the nitrogen is in the center. So this is the cyanate, and this is the fulminate. Draw 3 possible resonance structures of fulminate. Okay, so here we go. Now remember, with fulminate, it's C and O. And this is number 75. Fulminate ion is CNO negative, and nitrogen is in the center. Can you see that?
Right.
Okay, so A is 3 resonance structures. So how many electrons do we have?
4 plus 5 plus 6 plus 1 is 16.
16 electrons. 4 plus 5 plus 6 plus 1, 16 electrons. Okay, so can you see how this is how we're going to start?
Right.
Because nitrogen's in the center. And we put lone pairs on the oxygen first, and then lone pairs on the carbon. We do oxygen first because it's more electronegative. So now we have to decide, how do we get an octet on nitrogen? And there are 3 ways of doing it.
A single and a triple, 2 doubles and a single and a triple.
You got it. So there's 1. There's 2. and there's 3. And I'm putting little negative signs out here.
Mm.
Now, what happens when we assign formal charges? The nitrogen always gets a +1 because it should have 5 electrons, but it only has 4.
Right. So a carbon should have 4. So 1, 2, 3, 4, 5, 6, 7. -3.
No, on this one right here that I'm
Oh,
pointing at.
I wrote it down differently than you. I did the other one.
Oh, so you're talking about this one where my pinky is.
Yeah.
Yeah, that's going to be a 4, but it's actually got 7, so that's a -3, which means, oh, we're done with that one. We
And the
don't accept 2s or 3s.
Right. Right. So that one's out of the picture.
Yeah, it's done. We're done. I mean, no forgiveness on that one.
So the carbons that have the double bond have 1, 2, 3, 4, 5, 6 electrons. So they're -2, both of them.
Yep. And this one is a 0, right? So as far as I'm concerned, that one's done too.
Mm-hmm.
So that means we're left with this one here. Agreed?
Right. It has a +1 for the oxygen, or a -1.
And a -1 for the carbon.
Right.
Okay, so we drew all 3 resonance structures, but we just evaluated them at the same time.
Right.
Okay, on the basis of formal charge, decide the resonance structure with the most reasonable. This one right here.
Right. Because the formal charges are most similar to what we'd expect.
Yeah, because we don't like 2s and 3s. You know, if you have a -3, that means you're putting all the electrons kind of right there on carbon.
Mm-hmm.
And we want to separate them as best as we can. If you have a -2, again, you're focusing a whole bunch of electrons on carbon, and we want to spread them out. Besides, carbon doesn't handle negative charge very well. Oxygen does it much better.
Right.
Okay, so this is the best based on formal charges because we have no -2s or -3 formal charges. What else do we like about it? Well, we like the -1 on oxygen, right?
Right.
And so that's what we have to go with. Okay, C. Mercury fulminate is so unstable it is used in blasting caps for dynamite. Can you offer an explanation for this instability? Hint, are the formal charges in any of the resonance structures reasonable in view of the relative electronegativity of their atoms? So here, if I were to guess why this is unstable, it's because if either of these contribute at all to this, you're going to have a very charge-rich carbon, which is not cool.
I mean, but you're saying it's not likely for those two to occur.
No, they do contribute a little bit, but maybe 5% to the overall structure.
But that's still unstable enough because this is in dynamite, it said.
Yeah. Well, it's used in blasting caps. So this stuff is pretty unstable, and probably what happens is that it doesn't need any oxygen to react with. It'll just kind of rearrange, and it might very well form things like, I don't know, carbon monoxide and nitrogen dioxide or something like that. Okay, so here, unstable. Unstable because why? Because all atoms have formal charges. Right? That's what I would go with. Because what is the most stable structure?
Something that has 8 a full valence.
Nope, I say all of them have no formal charge, 0.
Oh, okay, that's what you mean.
Yeah, so
The
not
most stable is when the formal charges are what they should be.
when they're all 0.
Yeah.
So this thing is separating charge all over the place.
So if we don't find a 0, especially if in the resonance structures we find numbers like 2 and 3, that means it's pretty unstable.
Right. Well, we don't even like 2s or 3s. That's why I threw this one out and threw this one out.
Okay. So because we saw no zeros in the one we kept then.
Yeah. And we just couldn't come up with one where it was 0s all around. We just could not. You know, why did we not have this guy? Because this guy here, whoops, whoop. Let's see. Let's look at this guy. -1 plus, whoop, -2 and +2. No,
Well, there's no octet
nope,
on
I did that
nitrogen.
wrong. I did that wrong. -1 +2 and -2. There we go. Look at that guy. That's no better, is it?
No, because we don't have an octet on nitrogen.
You don't have an octet, and look at the formal charges.
Can you put it up a little? Right, and we have 2s.
Yeah. So, I mean, this was just the best we could do. We could not make it work.
Mm-hmm.
Okay, that's 75. Since I have some problems written out already, I'm going to look at some of those.
I think there was one more kind of group of questions I was struggling with.
Do you know about where they are?
Yeah, it was number 71-ish, I think. If I'm looking at it, I don't have like the questions written down, but it was when you have like where they would make the bonds, I think.
So here's one.
Yeah, with H plus. It right around there, exactly.
Okay, so here's a perfect one then.
Is that 70? Yeah. Okay.
Draw an electron dot structure for the cyanide ion, Cn -1. So we're looking at 4 plus 5 plus 1 for 12. Oh, 10. I can't add. So naturally, we're going to start with carbon single bonded to nitrogen. We're going to put the electrons on nitrogen because it's more electronegative.
Right.
And then we're going to put 2 more on carbon so that we have 10 total. And the only thing that really makes sense is to make a triple bond and have lone pairs on both carbon and nitrogen.
Right.
The only thing that makes sense. And here, this ends up being a 0, and this ends up being a -1. We would like the -1 to be on nitrogen, but there's no way to do it and get octets.
Okay. So right there, we can say that the H plus would go on the negative because of.
Yes.
Okay.
H
So I.
is going to be attracted to that. So when these two form a bond, what's going to happen is these 2 electrons will bond to the hydrogen.
And
you'll have that. And now let's look at formal charges here.
0 for hydrogen. +1 for, or 0 for carbon. 1, 2, 3, 0 for nitrogen.
Now let's put the hydrogen on the other side, okay?
Okay.
So we're going to pretend that the hydrogen would bond to this nitrogen with a 0 charge, okay? Let's look at the formal charges here.
Hydrogen is still 0. Nitrogen is +1. Carbon, 1, 2, 3, 4, 5, -1.
So does it make any sense for this molecule to make this and have this kind of charge separation? Or would
No,
you rather make this and everything have a formal charge of 0?
it would make more sense for the first one.
So this one's the winner, chicken dinner.
Okay, so you don't have to do like one by one, because I did it, the way I had to figure it was by making it a double bond first and then seeing that carbon still had space.
No, you do it based on your stable resonance structure.
Okay,
So for instance, if we had another one like this, now this has 3 resonance structures, but when we want to look at where the hydrogen would bond, where do you think it would bond?
on one of the negative,
Let's do 2 of them.
on either side.
That's right. That makes the most sense, doesn't it?
Uh-huh.
Let's look at the formal charges if we do that. Because the formal charges right now are -1, -1, 0, and 0. Now, how are they over here?
The hydrogens are 0. The carbon is 0. The oxygen at the top is 0. All of the oxygens are 0.
So there you go.
So
The lesson you're supposed to learn for number 70 and 71 is that, goodness sakes, the hydrogen is going to add to an atom with a negative formal charge.
and does that mean that it makes it more stable too, because the formal charge is now 0?
Yeah. Yeah. This is, well, no, not necessarily. No,
Okay.
no.
So can we do 71 with SO3 2 minus 2?
Sure. Okay, so number 71, SO3 2 minus, right?
Uh-huh.
Okay, and we're supposed to draw the electron dot structure for sulfite, and this reacts with H plus, so here we're going to have 6 plus 3 times 6 plus 2 electrons for how many?
26.
26 electrons. So we're going to put sulfur in the middle because it can make the most number of bonds.
Uh-huh.
And then we're going to put pairs on each oxygen, and that's only 24. So where do we put the last 2?
On the sulfur.
On the sulfur. Good. Now for this one, we can make a number of different types of structures, but this is probably one of the most common ones. So we'll make a double bond with one of the oxygens, just one to begin with, okay?
Okay.
Formal charge on oxygen with a double bond is 0.
Mm-hmm.
Sulfur, 0. This oxygen -1. This oxygen -1. So this is pretty good. We've got 2 zeros, right?
Right.
And let me tell you, when we have a -2 formal or -2 charge on this, we're going to have either a -1 and a -1 somewhere on it, or a -2 somewhere. What do we think of the idea of having a -2 somewhere?
We don't like it.
We don't like it. So here, this is about the best you can do. Okay?
Okay.
Now, we could do this. let's, doing it with one oxygen worked great. Let's do it with two, right?
Okay.
Okay, let's evaluate this. The oxygen with the double bond is still 0, 0. This one's still a -1. What's this guy got to be?
-1.
-1. So what do we think about a -1 on a sulfur instead of a -1 on an oxygen? That's the trade-off.
Right.
We don't like this because we like the negatives on the oxygen because it's more electronegative.
So this is kind of a tangent, but if we had like an SO4 2- and we added 2 H pluses to make the sulfuric acid,
Yep.
um,
Well, this is
they
the
could go on either of the oxygens because they'd all be.
this is the sulfate. Whoops. I made a mistake.
Oh, I'm forgetting to make the double bonds in my head then.
This is the sulfate. Negative, 0, 0, 0, negative. So where are they going to go on this guy? Here and here, right?
Right.
And this is better than this because if you do this, and I need to put a 2- here before I forget. Here you get -1, -1, -1, -1, and +2.
Wait, why is there a double bond here on the oxygen?
Which one?
For the
Oh,
SO4?
this should be a double bond. Whoops.
They should both be double bonds?
There should be 2 double bonds on this.
Okay, so the sulfur then is hypervalent.
Yeah, because it's in period 3. Anything
Okay.
in period 3 can be hypervalent. 3, 4, 5, 6, 7.
So, if we were to draw the Lewis structure of, any of the acetate, chlorate, whatever, all of those, anyone that has a hypervalent element in the middle, I guess how would I know? Do you just make it even if it can be hypervalent?
If it can be hypervalent, because you get better formal charges.
And because sulfur can have 6, it can have 6 bonds.
Anything in period 3 on up, 3, 4, 5, 6 can be hypervalent. And so sometimes hypervalent means this. So that's hypervalent.
Right. I mean, anything that can make more than 4 bonds is going to be hypervalent anyway.
Yes, but sometimes things that make 4 bonds are hypervalent.
Uh-huh.
This is hypervalent.
Right.
So why can xenon be hypervalent, but why is it neon can't? Because neon's in period 2, xenon is past that.
Right. And neon then is neon the only noble gas that can't make any bonds?
Well, I'll be honest with you. I don't know if anyone's ever reacted neon with anything successfully because it's really inert. Usually when you're talking about trying to get things to react when they shouldn't, bigger atoms react better because the electrons that react are farther away from the nucleus.
Can you remind me argon too? How many bonds argon can make other than 0?
Probably this.
Okay. So it can probably do 2 or 4.
Yeah, but argon, I'll be honest, I don't know if anyone's ever made any compounds with argon. They did it with xenon. They've done it with krypton, but I don't know about argon. The smaller the atom, the harder it is to get to react.
Okay.
Like when you look at the lithium versus sodium versus potassium, and you look at these guys reacting with water, there's videos on this, and they're kind of interesting. But and they're English scientists that are just having fun. They put lithium in water and it bubbles. They put sodium in water and it bubbles and sparks.
Uh-huh.
They put
Okay.
potassium in water and it bubbles, sparks, and turns into a flame and explodes a little bit.
Uh-oh.
Rubidium and the cesium, when they put those in water, they basically do it behind a plexiglass shield to protect themselves.
So they didn't want to try francium.
No, they may have done francium. I can't remember if it was francium or cesium. Well, one of them, they had it in a little vial that was protected so that when you put it in water, it would dissolve slowly. So they threw it into like a porcelain bathtub and ran away and filmed it. And when they were done filming it, the bathtub had exploded.
Oh my.
So,
Hopefully that was
so
enough.
why are these more reactive? Because they're bigger. And when they're bigger, the electrons on the outside are easier to manipulate because they're farther from the nucleus.
Right.
But if you're wondering, if you just want something to do because you're bored, watch videos where it says potassium with water, rubidium with water, cesium with water.
Mm-hmm.
And no, not everyone can do this. I can't do this with francium or cesium or rubidium. I can't buy these, but I can buy this. I can get potassium. And there is a story that one of our instructors actually wanted to demonstrate this to his class. So he took a piece of potassium that was like the size of a golf ball.
Mm-hmm.
And at CR, there's a pond. And so he took this golf ball sized piece of potassium and he had a gloved hand on it, latex glove, and he threw it into the pond. And because it's so reactive, it creates hydrogen gas, which ignites. The golf ball of potassium reacted with the water immediately and blew up.
Oh no.
The problem was that since it was golf ball sized and it blew up, it didn't all have the chance to react immediately.
Oh yeah.
So chunks were flying through the air. And actually, I think it was more like a baseball sized piece because he said there was a golf ball sized piece coming right at the class. And he thought, oh no, I'd better catch this one so no one gets hit by it. And luckily it fell short and fell into the water and it reacted
Right away again.
in fire and flame and all that.
I mean, it could have been like a fireworks show.
The students thought that's exactly what it was, a fireworks show. They were completely satisfied by the whole thing.
What color would that be?
The flame for potassium is kind of I want to say a purplish reddish type flame.
Right, so it did look like some scary fireworks.
Yeah, sodium is more of a yellowish flame. Have you ever seen the sodium street lights?
Yeah.
They have a yellow flame. So each of these elements has a different color when they ignite because what's happening is the electrons are going from lower level to higher orbit.
So that's what we've been learning then. The color.
When they come back down, they give off a particular wavelength of light.
Right.
So
that ends on the second valence.
Yeah. So each element has its particular spectrum and it's more prominent lines. And so that's the color that the flame looks.
Mm.
And that's how we analyze the composition of stars from so far away is that we're basically looking at their spectra and finding out what elements combined together make that spectra.
Okay.
And it's kind of complicated because you have to say, well, these particular wavelengths come from this, these particular come from this. And
how do you isolate?
It's complicated, but they can do it. With computers nowadays, you can do some amazing things.
That's pretty cool.
Mm-hmm.
So they can actually come up with the composition of some of these stars.
Right.
Or at least in the visible spectrum.
Oh, right. It doesn't even need to be the visible spectrum.
Well, they can calculate all of them.
Yeah.
They just won't see it. They won't see them.
Well, we can get the UV spectrum and we can get the infrared spectrum and still learn from them. Even though we can't see them with our eyes, instruments can. And we do have infrared and UV spectra for all the elements. So it's a pretty interesting thing.
So you could be given a bunch of information about something and ask, what element is this?
Yeah, well, I can't do that to you for this exam because it'd be too hard for you to do, but astronomers do it. And I'm sure that there's some sort of class where they're given that and they're told to do a computer analysis of it and figure out what the elements are.
Right. The most we have to do is the electron configuration. What element is this?
Right.
For the most part.
That's right.
Pretty
All
cool.
right, it's late.
Yeah.
So I
It's
think
time
we're
for
going to call it quits. Have you
All right.
taken the quiz yet?
I did. I took it last night. I have to do one more attempt.
To improve your grade.
Yeah, I guess I don't have to, but I
Well,
always do.
Why wouldn't you want to get a 10 out of 10?
Those are the only points I know I'll get. So.
Did you already get a 10 out of 10 or did you get like a 9 out of 10?
I got an 8 out of 10 actually.
Well, then you better go back and get 10 out of 10 for goodness sake.
That's what I'm gonna do.
Excellent. Okay. Thank you for calling in. I hope I was somewhat helpful.
Yeah. Thank you so much, Tony. Have a good night.
We'll see you later. Bye-bye.
Bye.